Yeah, so thank you all for coming for the second week. Today, we won't start with computer vision because we changed the schedule, as you know, but we'll start with audio domain. And audio is one of these cool topics that has two unique features. First one, apart from other topics, audio requires you to know some extra stuff from signal processing. You can't just take the input and use it as is. You need to do some pre-processing before, usually. The second part, the second thing is that usually nobody wants to learn audio domain because audio is computer vision plus NLP. So if you know computer vision and NLP, you basically know like 90% of audio. And we'll see why in a moment. And another cool thing related to the second one is that if you know audio, you know CV and NLP. So I like audio more. And today we'll cover a bit of theory and then some interesting tasks, like the basics for this task. And in the second part, we'll cover voice biometry, which is my preferable topic, which I work on. So let's start with what is sound in computer. Sound wave in general is just a pattern of oscillations, which is caused by the movement of energy through the air. And microphone picks up these air oscillations and converts them into electrical vibrations. These oscillations are converted into an analog signal, so it's like a continuous signal through time, some function x of t. And to actually work with it on computer, we have to convert it into a digital signal or discrete signal. So it will be a sequence x of n, not a continuous signal. So conversion happens using this analog to digital conversion technique. The first part of it is called sampler. We have our continuous waveform as input, and we just take samples from this continuous input. We'll see on the next slide how we do it. Given this discrete time signal, usually there is a quantizer that creates some floating points numbers that we can actually store in our computer, and coder will convert it to binary format, so computer will know how it works. We can ignore quantizer and coder today and just look at the sampler. And the sampler basically works like this. X of n is equal to x and t, where t is the sampling period in seconds. Usually you don't work with the sampling period, but with the sampling rate in hertz, 1/second, f, which is equal to 1/t. So sampling rate basically means the number of audio samples in 1 second. Here you have analog signal on the left and its discrete version on the right. And in computer, we'll work with discrete signal like on the right. Yeah, using some interpolation techniques, we can convert digital signal back to analog one. So we have a discrete signal like it on the right, on the previous slide. And using some interpolation methods, we can go back to a continuous time signal. We won't cover how we do it, but there are different techniques. And if you're interested, you can Google or look at Paolo Brandoni's course, Comp 202. There are some stuff about this. Let's move to spectrogram. No questions yet? Yeah. Okay. So when we work with a waveform or raw audio, there are several problems. First one is that 1 second of audio contains sample rate elements in it. And if you have a high sample rate, when we work with music, for example, which has usually 44 kilohertz, so 44,000 hertz sample rate, if you want to store 4 minutes of audio, like one song, it will be a sequence of lengths more than 10 million elements. In contrast, when we store one high resolution 1024 by 1024 image, we will need only 3 million elements if you have an RGB image, so with 3 channels. So when we work with raw audio, our computational costs increase severely. Another thing is that to store one letter, one sound, when I say like one A, in audio, I will need thousands of samples to store this just one sound. Here, there is an example with 22,000 hertz, and we see that to store some different sounds, we need a lot of samples to store. Also, this visualization as a waveform is similar when we use some transforms. For example, here is voice on the left, and here is voice plus some noise on the right. Just by looking at the second picture, you can't understand whether this is voice plus noise or whether it's just voice which has high amplitude. Like, maybe I'm screaming and that's why it looks like this, not because there is some noise. So to mitigate two of these problems, usually we don't work with raw waveform, but with time frequency representations. So what is frequency? We need something apart from temporal representation to better understand what happens inside the audio. And frequency domain is just another domain to represent audio where it's a type, I guess, where some things may become clearer. So you said that you all know signal processing a bit, so you know Fourier transform. Sound is the sum of sinusoids. So using Fourier transform, we can change the basis of our audio from standard basis to basis with sinusoids. And Fourier transform basically does this. It's a change of basis in the vector space. There is a complicated formula here with an integral. And if you look at the picture on the right, we see that we have a waveform here in time. We can say that this is a sum of three sinusoids, like this one, and this one, with amplitudes corresponding to this peak, plus this peak, plus this peak. So to get this audio waveform, we need to sum this sinus multiplied by this amplitude plus this sinus multiplied by this amplitude plus this sinus multiplied by this amplitude. Let's look at the GIF here. So we have our waveform. We see that this is sum of some cosine plus sinus. And we just write what are the coefficients for this sinus and for this sine and cosine to actually create our waveform. And now for Fourier transform, we return a thing like this, where we have magnitude and phase for each cosine. We'll see in the next slide. Yeah, one remark here is that the output of Fourier transform is complex by design. So because we have sine and cosine, which is according to Euler's formula is e to the power of minus e something something, the result is complex. And also because in audio we work with in audio deep learning we work with discrete signals, we'll have a discrete version of Fourier transform which looks like this. Yeah, it's the coefficient from a raw waveform multiplied by e to the power of something. Yeah. So here is an example for one waveform, which is 10 sinus something plus 3 sinus something. And imagine our sample rate is 2 kilohertz. Then if you go back from waveform version to frequency domain, we'll have something like this. And we'll notice that there are two peaks here, which indeed corresponds to the frequencies which are in this sinus 1 and sinus 2. Notice that we also have something here. So actually, Fourier transform returns us a symmetric output when we have a real input. So our waveform is real, and because of this frequency domain, we'll have like this pair and another symmetric pair to the center, or to the zero if we consider negative frequencies. Yeah, so usually we throw the second part away just to save the memory and computations because it's symmetric, like we don't get new information from this part. Frequencies allow you to easier distinguish some transforms. For example, here is a sum of sinusoids with noise, and here is original sum of sinusoids. And if you look at the waveform, you can't actually understand whether picture on the left has some noise or not. Like you see, there is some distortion, but it's harder to see. But if you look at the frequency domain, you will notice that for original signal, you have 0 magnitude here, and for noisy signal, you have a lot of small peaks here. So this means that you have many random frequencies, which corresponds to white noise, and you understand that this signal on the left is probably sum of sinusoids plus white noise. Yeah, but frequencies may rapidly change through time, and if you have a long audio signal, we want to actually see what are the changes. So in practice, instead of working directly with raw waveform or just raw waveform in frequency domain, we work with a time frequency domain. So we want to see both changes across time and changes across frequencies. Usually they look like this. On the x-axis, there is time. On the y-axis, there are frequencies. And if we go from left to right, the darker the color, the less energy we have. So darker color here means like silence. And we see that our audio starts with some silence, then there is some speech, and then some more silence. And according to frequencies, we see that we have a lot of energy in low frequencies and small energy in high frequencies, for example. So how can we create this image? We have such thing called short-time Fourier transform. We look at some window of a certain length and apply our Fourier transform on this window. And this is our first column of our STFT. Then we move this window by some step, also known as hop size. Note that they overlap. So we shift our window a bit, compute another Fourier transform, and this is our second column, and so on. The problem is that when we use these shifts, if we don't change the signal, we will have rough borders. So if we shift with overlapping, the place where they overlap will be counted twice with a high energy, and it will corrupt a bit the result. So usually you apply, before calculating FFT, you apply so-called window function. There are several versions of this window function, but the idea is that this is some function which is close to 0 at the corners, and in the center it is equal to 1. And it will smooth your window a bit and will mitigate the problem that your windows are overlapping. So basically, you go with these windows through your signal, calculate discrete Fourier transform, and stack columns with this discrete Fourier transform. Maybe picture on the right is more cleaner. So you have your sequence, you have some windows with some hop size here, and you stack these windows into Fourier transform arrays, which will create you a matrix. So because Fourier transform is complex, the output of my STFT is also complex. And usually we don't want to work with complex numbers because it's complicated. And we work with magnitude, so the absolute value of each complex number, and with the phase, so argument or phase of the complex number. So from STFT, which is complex, we can get magnitude spectrogram, which is real, and phase spectrogram, which is real. However, notice that picture on the left has some structure. So we see that something happens. It's much cleaner. And phase spectrogram looks like some noise. It's not noise because we know what phase means.
No.
What's phase? So if you have a complex value, like this in an Euler's form, so this is your magnitude, and this is your phase. Yeah, so
it is 2 pi, 4 pi.
yeah,
In terms of like the signal.
yeah. So this will look like sinus of, like, I don't want to lie, but it will be something like this here. Yeah.
Signal, like where exactly it looks like, is it a condition of X when it's like going, like for example for signals?
So,
amplitude, okay, I got it. But what about the phase part?
You have a signal that starts exactly at the same time. So you have a sinusoid that's got a frequency here. 10 hertz. Starts exactly at 19. And then you have another one that starts at 19 plus half.
Oh, all right.
And that's, I don't know whether that's plus or minus. I think it's minus. Well, if it's exactly half, you can't tell the difference. So I've chosen a good example. You start a little bit later, but the shape of the wave doesn't make any difference, but in time it's shifting.
Yeah, so
right, and then in the phase direction.
maybe it will be easier like this. So imagine this is a complex plane. So here is imaginary part, real part. Yeah, so phase means what is the angle here.
Okay.
And amplitude means how long is your signal. So is it like this with a high amplitude, or is it like this with a small amplitude? Hope people can see. Yeah, and so if we have A plus IB, like a complex value, to calculate magnitude, we will calculate the absolute value. And to calculate phase, we'll calculate the argument of A plus IB. So, like if it's A plus IB, this will be our phase. Yeah, so notice that we apply this absolute value and argument calculation element-wise. Yeah, so we have a complex matrix, and we element-wise we apply absolute. We take absolute value to get magnitude spectrogram, and argument to get phase spectrogram. Also, we don't usually work with raw spectrogram. We take the log of it because it's easier to interpret by humans. If you look at the picture on the left, you see only frequencies with high energy here, and you don't actually see what happens at the high frequencies because the difference in energy is too severe. But if you take log, everything becomes much cleaner, and it's easier for humans to understand. And also, we believe that it is easier for deep learning models to understand, because when the input can have two distinct values, it might hurt our deep learning model. Yeah. So STFT also allows us to see noise. We'll see it in a couple of slides. And also, we can see some other useful stuff from STFT. For example, the speech signal will contain harmonics, which can be clearly seen in the STFT. Here, for example, we know that this is speech, and we see here that there is one frequency, then there is another frequency above, and actually that's how harmonics look like in a Fourier transform. Also, if we look at these frequencies and look where the peaks in frequency domain, which we'll refer to like F1, F2, we can actually understand what letter, what sound we said in this period. These peaks are called formants, if you want to Google it. And for example, letter A, when I say A, the peaks will look like one shape, and when I say E, the peaks will look in a different shape. and if our deep learning model will be able to find these peaks and understand what peaks correspond to what letter, we can actually get text transcription from this spectrogram. Questions? Yeah. The color is what? Magnitude. Yeah, so the higher the value here, the more energy we have. So low values correspond to something which is closer to silence, like nothing. And high values correspond to high energy points, where I start speaking, for example, and so on. Yeah. Notice that Fourier transform is just a change of basis. So Fourier transform on its own is invertible. So if we go to frequency domain, we can go back to time domain without any losses. Given some constraints on window and hop size, which are called NOLA or COLA, non-zero overlap and add, something like this, the STFT transform will be lossless. So we will be able to convert STFT from this back to raw audio. Picture is not correct here in a sense that you can't go back from just magnitude. You need to take phase back. When you have phase and magnitude, you can again calculate the original complex value spectrogram, and then you can invert the STFT. Okay, good. Yeah, one thing here is that humans usually operate in mel scale, so in log scale, in the sense that for human ear, usually we can clearly hear what is the difference between 500 hertz and 600 hertz, but for 5,000 hertz and 5,100 hertz, the difference is much harder to actually perceive. So we also can use mel spectrogram for deep learning models. And it's also related to how humans hear, and we believe that maybe a deep learning model will work. It will be easier for the deep learning model to work with mel spectrogram. So how we do it? We have our magnitude spectrogram on the left, and we have so-called filter bank. So filter bank is several triangle shape sequences. No, triangle. Thank you. Yeah, so you have several triangles here, and each triangle defines what is the weight. Let's, for example, see the first triangle here, the blue one. It will look here something like this. So you have like triangle here and 0 everywhere else. Oh, no, sorry, I was wrong. It will be applied to frequencies. Let me maybe write it. So you have your spectrum, and we have triangle here, which will look like this. Yeah, so 0 everywhere here and 1 here. So every frequency will be multiplied by every row, in our magnitude spectrogram will be multiplied by the value in the triangle. So this one will be taken with 0 weight, this row will be taken with weight 1, and this in the middle, for example, with like 1/2, something like this. And with one triangle, we can calculate one STFT matrix. Then we change this triangle to another triangle, which will be a bit shorter and a bit wider. So shorter in this way and wider in this way. And we'll again calculate another matrix and sum it with the previous one. Then we'll calculate another triangle, and so on. So these triangles look kind of like log scale if we look at the highest value here. And if we sum all of the triangles, we will get our STFT matrix in mel scale format. So actually what we do, we compress the y-axis. We don't do anything element-wise. So if our matrix was n by m, instead of returning something which is n by m, we will get something which is equal to the number of triangles by m. Okay. Yeah.
The middle figure there shows frequencies ranging from -500 to +500.
Yeah, I guess it should be. The picture is a bit incorrect. So I guess yeah, it should start from 0 to like sample rate over t, like this. Yeah, I guess it should be like this, and let's say that this is a typo. You had the same question? How triangles are calculated? I don't remember actually how was the equation, but
Is it the same area in each triangle? Looks like they're wider the
wider and shorter, so yeah, maybe that there is the same area. You're right.
I'm not sure, like we used to have other functions, but the idea was more about the frequency range. So that, for example, every time when you are using certain frequency, it was not about the height, but the range. For example, if I would be interested in alpha, let's say wave, I'm like, okay, it's from 0 to 10, from 10 to 12. So that's why maybe you just should think about it just in terms of frequency.
Yeah, I don't want to lie here. Yeah, but the idea is that we will have triangles which are wider, and they're wider because if you look at the log scale, in low frequencies, we will have small buckets, and in the high frequencies, we'll need wide buckets to actually capture the difference which a human can perceive. Yeah. And after calculating this weighted split, we will calculate our Mel spectrogram and also take the log to see clearer what happens. And we see that it looks kind of like a STFT, but a bit corrupted, a bit different. But in terms of how you can perceive it, it's easier for humans. Yeah, so a remark that we want to make y-axis look like it's in log scale, not just taking the log of elements in the spectrogram. Yeah, I told this when we refer to the shape. Yeah, and in general, time frequency transforms look like this. You have some matrix which is equal to the sum of x at some point multiplied by the vector at some another point, where these vectors are called analysis filter, and n is the number of filters. K is the number of frames. So when you do this hop size, one column in your STFT is one frame. Note that here frequency is not frequency in a Fourier transform sense. So it's still called time frequency transform. But if our un is not like e to the power of something, this won't be frequencies in a standard sinus sense. We will just call them frequencies, but it will be something else completely. And depending on which type of UT you have, these time frequency transforms are called differently. If you learn UT jointly with your deep learning model, so UT is trainable, filters are called free. We'll see an example today a bit later. If UT belongs to a family of functions, which is defined by hyperparameters, so we say that your UT depends on like two parameters, f1 and f2, and your model learns only f1 and f2, and the UT is calculated using this f1 and f2. These filters UT are called parameterized. We'll see example today in the second part of the day. And if UT is handcrafted, filters are called fixed. So in STFT, UT is just e to the power of something, then e to the power of something, e to the power of something. So they're handcrafted, they're fixed, and the model doesn't change them anyhow. Yeah, from the introduction to audio signal processing, that's all. Do you have any questions so we can continue? Okay. Yeah, so deep learning audio has large number of different tasks that are presented on this slide. From speech synthesis point of view, you have text-to-speech, which converts text to speech. You have voice cloning. I guess it will be on the next slide. Yeah, let's go like this, sorry. So let's look at speech analysis at first. There is speech to text. You have speech and you want to get text transcription from your speech. There is voice activity detection, given some speech sequence. So you want to understand where there is silence in this sequence and where there is actual speech. Voice biometry, which we'll talk about today, and actually anti-spoofing here, define what a speaker is talking right now. So is it like, does this speech belongs to like me, or for example, for you, or for you? Yeah. And anti-spoofing is when we try to copy my voice, for example, using some deep learning algorithms or not deep learning algorithms, which which you can kind of hear like it's my voice, but it's actually not mine. I never said this. So that's called fake detection or anti-spoofing. Also, there is keyword spotting, which we discussed previous week. It's used in voice assistants when you say, hello, Siri, and your model need to get that you actually said the word Siri, this keyword. It's called keyword spotting. Speaker derization, when you have several speakers which are talk one after another, and you need to say that in this time frame, speaker number one is talking, in this time frame, speaker number two, then speaker number one, speaker number two, and so on. So you separate unmixed speech into several utterances. And there are some classification tasks like what is the age or gender or emotion of the speaker. In speech synthesis, yeah, as I said, there is text-to-speech. Voice cloning, when you get my voice, but try to make it sound like I said something else, so the same speaker, but other text. Voice conversion, other speaker, but the same text and intonation. So I say something, and then the model makes it sound like some president says the same thing. For example, voice singing, when we want to create a voice that sings some vocals, and speech denoising, when we have speech plus some noise, and we want to get clean speech from this. Also, there is speech separation, which is kind of like speech denoising, but instead of noise, we have several speakers talking at the same time. Yeah, and now let's go through some tasks and try to understand the general idea how they work, how to solve them. I think it will be more interesting than, in contrast to focusing on just one task at a time. So speech denoising, also known as noise suppression tasks, can be solved like this. The common approach is you create a model that outputs some mask which is applied on a time frequency representation. So you have this STFT plus noise, and you apply some mask, just multiply your magnitude by this mask, and you get clean magnitude. And your speech is denoised. Speech separation task, which is about separating speakers, so when two speakers speak at the same time or many speakers speak at the same time, can be solved in a similar manner. So you have a spectrogram with two speakers, for example, and you apply mask on this spectrogram to get speech which contains text only of speech only from the first person in your audio. Yeah, one of the models for speech denoising is called DC-CRM. I don't actually remember what is the full form, like deep complex convolutional recurrent network, something like this. And it is an interesting solution because usually, as I said, engineers use only magnitude spectrogram because phase spectrogram looks kind of random and you actually don't know what to do with it. And also, you can't work with complex values because directly, because it's complicated. So we want something real and we choose magnitude spectrum. But some networks can work with complex STFT directly by applying complex versions of the original models that we discussed previous week. Like we will have complex convolutions, complex RNN, LSTM, complex fully connected layers, and so on. So let's discuss an example of a complex convolution. It's actually simple. So instead of having one input, which is complex valued, we will have two inputs, the real part of our value and the imaginary part of our value. Then we can modify our convolution to look like this. Instead of having just X convolved with weights, filter weights, we will convolve real part with weights for the real, with real filters, sorry. We will subtract imaginary part convolved with imaginary filter, and it will be our new real part. And our new imaginary part will look like this, but the filters are changed to are opposite. So we will have a real input convolved with imaginary filter and imaginary input convert with a real filter.
So they have the same magnitude, but it is just one multiplied by imaginary, right? Like it's not like A and BI, it is like A and AI.
I didn't understand what you...
I mean, when you're saying real and imaginary, does it mean that they have the same magnitude?
When I say real imaginary, I mean that you have A plus IB. This is a real part, and this B is the imaginary part.
I know, like imaginary because you are multiplying by this imaginary I. So question is weight of this A and B, are they same or are they different?
Weight, you mean was the field?
The magnitude, the numbers.
Yeah, no, it depends on what you had in your complex STFT. So the A plus IB are the output of your complex STFT. A and B can be like any. Yeah, and you take only A's to create a real part of STFT and only B's to create imaginary part.
Yeah.
And then you process like this.
Yeah.
Fine? Good. Good. Yeah, for complex LSTM, the idea is kind of similar. We won't cover it today. You can look at the original paper, like there is another equation or two equations, but the idea is exactly the same. One note that PyTorch versions, which are kind of new, like I don't know, maybe 112 or 113, starting from 113, they can work directly with complex tensors. So maybe you don't actually need to create this complex convolution yourself, and you can just pass complex input and PyTorch will calculate the gradients automatically. But I never saw someone actually do it like this. So maybe it doesn't work good enough, and you should try. And if it doesn't work, try something like this. Yeah, some researchers, instead of thinking how to work with complex values, they try to create this trainable UT, as I said, which are not like STFT based, but your time frequency transform is trainable, completely trainable with your network. So instead of having STFT, you will have an encoder, which is just some convolutional layers, stacked convolutional layers. And your encoder will output something which is look like batch size multiplied by channels, multiplied by height, multiplied by width, something of this shape. Then another part of your model will calculate the mask, and you will apply this mask on the output of your encoder, and your decoder will convert this STFT-like representation back to the audio domain. So one paper which does this is called DMUX from Facebook, and encoder basically is just some convolutional neural network. Masking is done via LSTM, and decoder applies thing which is called const transpose. If we have time, I will cover what is it today. If we don't, I guess Federica will cover this on Thursday. But const transpose incorrectly can be seen as an inverse of convolution, but actually it's not nothing like this. Const transpose is just a thing which tries to upscale your input back to the original dimensions. So as you remember, your convolution, or in this example, you have like an audio which is long, but you using convolutions, you create something which looks like this, which has a time length much shorter than the original audio input. Now your decoder wants to go back from T nu to T. In order to do so, it needs to somehow upscale this to this. It's like an interpolation technique in signal processing, but const transpose is a bit more advanced. So it's just a technique to go from T nu to T via some interpolation-like stuff. Yeah, so DMUX look like this. I hope people on Zoom saw this, yeah? Yeah.
It's 2D.
No. So your original audio was 1 by T. After encoder, you got something which looks like C by, let's say, like frequencies, but it's not actually frequencies. So you will have C by something which looks like this matrix, and then your const transpose network will move C back to 1, and guess F to 1, and T nu it will try to upscale this to T.
You know, when you're saying frequency, which is not frequency, what exactly you mean? Can you give an example of what it could be?
So when we apply the real definition of frequency is using Fourier transform when we have sinus of something, yeah? So our UT in this equation will look like e to the power of 0, like e minus I, like 1 over n e, something like this, e to the power of I, 2 over n p, and so on. So if you apply this UT to this equation, you will get short time Fourier transform. And because you actually use something which is Fourier transform based. So this is basically a basis of a Fourier transform. You will get frequencies in the sense which we discussed before. But if your UT is just V1, W1, W2, Wn, and you use this equation, you will get some matrix, but you can't say that what you got here have something to do with this.
So are they just weights?
So these are just weights. Yeah, but because the output will look like this matrix, where on x-axis you will have time, and on y-axis you will have something, which is created by an equation which is similar to original STFT. We still call it frequency, but it has nothing to do with frequency transform. Yeah, so Fourier transform. So if we have sinus with some frequency, we will know that its frequency is indeed like theta. But if we calculate and we will get theta from Fourier transform. We'll have a peak somewhere close to theta. But if we apply something like this, we won't get something as theta. We'll get something else which has nothing to do with theta. So it's called time frequency transform with the star just because it has a similar equation. Good? Good. Yeah. So
In the bottleneck, you have for the masking for the
LSTM.
And why is there an arrow? I mean, what does it mean where you have an arrow from out S to T to N?
This one, you mean?
The encoder one, yeah, there. Well,
It's just fancy visualization that this is like a recurrent neural network. Something as you remember, your recurrent neural network.
Okay.
Yes,
It's not symbolic of a different.
No. So your recurrent neural network can be visualized like this. And just to have a fancy visualization, they say, let's put L here, S here, T here, and so on. Yes, the questions are for Facebook, why they did so.
If I were reviewing that, I would tell choice. Because there's no recurrence in that. That's a stupid way to try and show that there's a recurrent human. But it doesn't matter.
Yeah. Yeah, so some of the models can be applied in streaming, and recurrent neural network are very helpful when we want to do some streaming. For example, you have a long sequence, long utterance. You can't just pass 4 minutes of speech to your model. As we discussed, it will be like 10 million. Input will have like 10 million elements, which is quite a lot. It will be hard to process. So instead of working with the long input, we chunk it. What I mean by chunk, we'll look only on the short time frame of your original audio input. And demux will work like this. It will take this chunk, encode it, pass it to your recurrent neural network, decode it, we have something less noisy. Then we will take overlapping chunk, we'll shift it a bit, apply encoder, we'll paste it back to recurrent neural network. And one useful thing here is that we can pass hidden state from our previous inference of RNN to our new RNN model. So as you remember, in recurrent neural network, we have X1, X2, X3 here, and this is called like H1, H1, H2, and so on. And the output will be H3. Usually when we start working with our recurrent neural network, here we have H0, which is usually set to 0. But when we work with the second chain, instead of having H0 equal to 0, we set H0 equal H3. You see? So this allows us to process chain number 2 with the information from chain number 1. So instead of using information only from our current chain, we can utilize information from previous steps. And we continue doing this chaining process, and then we can denoise the whole audio. When we work with keyword spotting, as we discussed previous week, we can do the same thing. We can listen to the chunk and hear, do we have a keyword in this chunk? If no, we move to the second chunk and so on. Yeah, and I forgot to say here, sorry. So notice that our task actually looks like a segmentation task. So we want to understand, to create a segmentation mask for our image-like input. And that's why doing speech denoising is kind of similar to segmentation task in computer vision. And if you know how to do denoising, you know how to do segmentation task in computer vision. And vice versa. If you know how to do segmentation task in computer vision, you can do this kind of stuff. And here in DC-RNN, you see a lot of errors like this. It's not about residual connections as we discussed previous week. It's actually something from architecture which is called UNet, which we will discuss on Thursday. But I just wanted to mention that notice how you could work on UNet in computer vision, never work on audio before, but you still can apply the same architectures. And that's why on the first week I said that don't try to work only on computer vision or only on NLP, because you can work on something and take the ideas from one domain to another. People worked on UNet in computer vision and then took it to audio. Yeah. So with speech denoising, that's all. Let's move to another task called automatic speech recognition. In automatic speech recognition, or speech to text, there are two types of designs for solving this task. First one is called CTC, and another is called transducer. There are also some models that use hybrid format. And we won't cover transducer and hybrid today because they're complicated. But CTC is relatively easy. So in CTC, you have a vocabulary of size V big, which contains all possible tokens. So in a simple case, you have your alphabet, like A, B, C, D, E, and so on, and the space character, space char. And your vocabulary contains your alphabet and this space. Given speech input, you try to return a tensor of size T by V, where T is the number of frames in your audio, and V is your vocabulary size. So for each row in this tensor T by V, you will have a probability that corresponding token is set at time step I. So imagine you have like your STFT spectrogram of size T here. So for each column of your STFT, you will predict P1, P2, and so on, VB, which are the probabilities. P0 is the probability that the zero token from your vocabulary is located in this column. P1, the probability that the first token contains in this speech, this column, and so on. Sorry. So you will get a table of probabilities for each column. And then when you get this matrix of probabilities, you can decide based on these probabilities what is the most probable output sentence. So how to combine these probabilities, these letters, so we can get the most the sentence with the highest probability. And one of the possible ways here is, let's take the maximum probability for each column. Like, for example, here P1 is the largest. Here maybe like P10 is the largest, and so on. Here maybe P0. I will say that our output is token number 1, then token number 10, and so on, token number 0. And then we'll convert them back to our letters. Token number 1, maybe this is like A. This is maybe, I don't know, like K. And this is, maybe this is a space, yeah? So, and our output sequence, our sentence will be A, K, something, space. Okay? Apart from doing argmax, there are some other techniques. We won't cover them today. I don't know if people saw it here. Yeah. So we can't do it there might be some problems with doing it just like I showed you, because if we split input into frames and classify each frame into num letters classes, and then one thing we will get that because one letter can be heard in several time frames, as we discussed, to say letter A, I need 2000 time steps in row waveform domain. Maybe 2 columns of our STFT will contain the letter C, and 3 next one will contain the letter A, and the last one will contain the letter T. So CCAAT is not a real word, and we understand that maybe one letter was spoken for more than one time frame. So let's merge them. We can merge them and get cat instead of CCAAT. The problem is that what about hello? So if we have the hello here and merge all consecutive letters, instead of hello, we would get hello, like with one L. So we need somehow to distinguish whether we need to merge 2 consecutive letters, or we need to take, or we don't, of these 2 consecutive letters, which looks exactly the same, are different in our final output. So how to do? So we add special token, which separates the letters. So our output now may look like this: HH, E, special token, LLL, special token, LLO. Then we merge the letters, consecutive letters, which are not separated by this epsilon special token. And now you see that we have L here, which are separated. Then we just remove this empty token, and now we get hello. Yeah. The special token is added to our vocabulary. Yeah, so instead of predicting space plus alphabet, we predict space, special token, and alphabet. So for each time frame, it can predict either letter, either space, or either special token. So our model will learn to predict special token instead of predicting letter. To do so, we will use this CTC connectionist temporal classification loss function, which will tell our model that you need to separate some tokens with this epsilon. So to predict for this time frame, you should predict special token, not actual letter or space. Okay. Yeah. Yeah. So if you want to get the word cat, you have several possible valid alignments, like this one, or this one, or this one. They will result in the same word cat. But notice that this alignment is not correct because this C and this C are separated via epsilon, and you will get CC80 instead of cat. Here, the problem is that you didn't predict anything for the last time frame. So each time frame has to have at least one predicted token. Oh, sorry, not at least one, exactly one predicted token. And here you had epsilon, you have T, you have C, but you don't have an A. So again, a wrong alignment. So how? Oh, shit here. Yeah. So again, let's look at the whole algorithm. We have an input sequence, which is like a spectrogram. For it can be a spectrogram, it can be raw audio, but for now, let's say that this is spectrogram. This input is fed for some model, for example, recurrent neural network. And for each token, for each time frame, sorry, it predicts the distribution over the outputs, over our vocabulary, including special token. If our vocabulary has only H, E, L, O, and epsilon, like this small vocabulary, our output will look like this. And the depth of the color defines like what is the probability. So the more white is the color, the less probability is predicted, and so on. Yeah, and then we will calculate all possible paths from this probability matrix and look at what alignments we get. So one path may look like this, HA epsilon, LL epsilon something. Another may look like this, another may look like this. And all these paths have different probability, which is calculated by a simple equation in yeah, so something is 0. Yeah, it is basically okay, it will be something like a Markov chain, I would say. That this is fine as I remember. So you will have something like this, and probability of your final path will be this.
But for this distribution to know that it has higher chance, does it mean that your vocabulary should have also words, or is it more like your vocabulary, does it consist only of sounds, or does it consist also words?
It can, so in a simple case, you only have letters from your alphabet, not phonemes. So like it's not like you have A, which sometimes is like A, sometimes is like A. You just have A. Another thing is called byte pair encoding, which we won't cover today, but it allows your model to actually learn to add pairs to your vocabulary. So instead of predicting A, B, like A and B, you will predict A, B as a whole token. And this is used when you have like CH, which sometimes can be like CH, sometimes CH can be like in character or ch in cheese and so on. So this will help your model to understand that sometimes a pair like CH can have different sound. Yeah. So your function will look like this. You will compute the probability for each path, and then you will marginalize over the set of valid alignments. So all alignments that indeed correspond to your target text, to the word hello, and that will be your predicted probability. And your loss function aims to maximize this CDC conditional probability. So this means that your model should predict proper paths, valid paths with the highest probability, with a higher probability than incorrect paths. So it looks complicated how to calculate this because we had we have a large vocabulary, we have a lot of time frames. It's hard to calculate it, but here is one of these rare examples where actually algorithms 1 course or algorithms course 2 course helps. So you can solve this with a dynamic programming algorithm, which basically means that instead of calculating the whole path, we can calculate the start of the path, and if our path is longer, we can calculate it more easier given the output of the calculation for the shorter path. Yeah, for example, P of prefix equal cat is the sum of P prefix equal cat and the last character is T, or plus P prefix equal cat, last character is special token. So these two paths will give exactly the same alignment cat. So we can say that this is our sum. And for example, for last character, last char equal T, we can say that it also looks kind of like this. So using these equations, we can calculate CTC more effectively. We won't go into deep details about this. Because in PyTorch, you don't care how it calculates. You just import CTC loss from torch.nn, and you calculate your loss passing 3 or 4 variables. The first one is predicted probabilities. So for each time frame in your batch, you predict the probability over the vocabulary. You pass the targets, which is encoded text, batch size multiplied by S, where S is the maximum length of tokenized text. So as parser will tell you in NLP, you can tokenize text in a different manner. And different sentences will have different tokenized encoded version, encoded lengths. You will pass them to the same length, S, to the maximum length, in order to process them. And because they are padded, you will also need to pass target length, which is the actual length of the target without padding. And input length, this is exactly the same thing, but for inputs. So if you have audio of different lengths, you will need to pass them to get batch. And here you say where your model should look like, where your loss should look like, to avoid consider padding as a valid stuff. Yeah, and model-wise, there are different architectures. One is called deep speech. It's from Mozilla, as far as I remember. It's pretty old, but gold. So it works like this. You have spectrogram. You go over it with sliding windows. And each window is processed by multi-layer perceptron, so some fully connected network, plus bidirectional LSTM. So I guess parser didn't tell you about bidirectional, But in your recurrent neural networks, you can go from left to right, and then you can go from right to left, backward. Oh. Yeah, so the idea of BLSTM is that you go from left to right and from right to left to actually see the whole context. So, so your most left word will be processed with the context from the most right word and so on. This speech too, you had a question?
Because I don't, if you're doing this in real time, then you can't.
In real time, we can't apply bidirectional recurrent neural networks. So if you want real time streaming, you need to apply unidirectional recurrent neural networks. But if you work on offline and you want to improve the quality, bidirectional is better. Yeah, and this speech too, exactly the same stuff, but instead of doing fully connected network at the beginning, they apply convolutional neural network, which is much more efficient, also better utilizes local context and so on. And the state-of-the-art method is called conformer, which is based on transformer. And it's exactly the same as vanilla transformer, but modified with an additional convolutional model here. So in your vanilla transformer, you have exactly the same picture as on the right, but you won't have this convolutional model. So convolutional model looks like this, is just layer null plus some fancy convolution, some fancy activation. So instead of ReLU, they have GELU, another fancy convolution, batch norm, another fancy activation, another fancy convolution, and dropout, which we talked a bit previous week, which just some stuff used for regularization during training, which tells that some neurons are not used via this forward step with some probability. Yeah. So what are the fancy convolutions here? The first one is called depth-wise. So as you remember, when you have input with several channels and we have one convolution, vanilla convolution will output you one channel. So it will process the whole input with one filter and output one channel. One filter will output one channel. In depth-wise convolution, each channel in the input will be processed on its own, and instead of summing the results altogether, we will say that now our output has 3 output channels. The same number of output channels as the input. So in original convolution, we summed the result, this output. In depth-wise convolution, we stack them. Point-wise convolution is just the standard convolution, but with 1x1 kernel size, which is required only to change the number of output or input channels. So to compress or expand your image-like representation. That's all for speech to text. Now you know 2 tasks, at least the basics. Let's move on. Yeah. Yeah, I guess we have some time. So text to speech. In text to speech, you want to do an exactly opposite task. You have some text and you want to create a waveform where some robot says exactly the same text you told it to do. So how it works? You have your text. There is text front end, which normalizes text somehow, so removes upper cases, maybe remove some commas, all this stuff. And instead of working with letters, you work with phonemes because it's easier to produce sounds from phonemes. Like given a letter A, it's hard to say whether it is A or A. And grapheme to phoneme will help you with this. So you will pass your text to actually get the phonemes, the phoneme transcription, And your model will use this phoneme transcription to actually create an output utterance. Then text-to-speech models can be end-to-end, so they can use this text to directly create a waveform, but it's much more complicated task. So usually you separate one model into two and train them separately. The first model will try to transform text to a Mel spectrogram, and the second model will try to transform Mel spectrogram to waveform. You might ask me why we can't apply just inversion of STFT here. Like I said that STFT is invertible. So there are two problems here. First one, we don't have a phase. And the second one is that we predict Mel spectrogram, not STFT. And because of this filter bank, these triangles, we have a compressed representation. So it's not lossless, it's lossy. So we can't go from Mel spectrogram back to raw waveform without losses. And wave synthesis is a deep neural network which tries to actually go back from Mel spectrogram to raw waveform with as precise output as possible. Yeah, we won't cover Mel synthesis today because it's complicated. You have some fancy transformers which do complicated stuff. And I don't want to talk about this, sorry. So let's do wave synthesis instead. Yeah, so Mel spectrogram is not invertible, but we can use some models to generate raw audio from Mel spectrogram. And one of the common approaches, actually the state of the art, is to use generative adversarial networks, GANs. How many of you know about GANs?
Yes.
Maybe, okay, good. So let's talk about GANs a bit. So in GAN, you have two networks. The first one is called generator, and another one is called discriminator. What they do? So discriminator tries to solve binary classification task. Given real examples from your data set of fake examples which were generated by your generator model, discriminator tries to understand whether this sample is from a real data set or is it a fake sample which was generated. Generator, on the other hand, tries to generate as realistic examples as possible. So discriminator won't understand that this is a generated stuff. So they play a game, two players game, where one tries to understand that generator, this is a generated image, this is a real image, and another tries to make discriminator believe that its output is real. So because you train these models together, at the beginning, your generator predicts something which is easy to distinguish from fake, from real. But because your discriminator will know that it's fake, generator will say, okay, I need to improve the quality of my prediction, and I will update my weights, so my generation looks much more like a real example. And then discriminator will see that there is updated generated version and say, okay, your prediction is still not good enough. I can still classify it to fake and real, improve some more. And they will learn together. One will try to fool another. One will try to understand that another is fooling him. So this is called min-max game. Generator will try to minimize this loss function, and discriminator will try to maximize this loss function. So PD is the probability, is the distribution of real inputs. Z is distribution of noise. So I forgot to say that originally GANs generate something from some noise distribution PZ. So not from some other image, but from a random noise. Yeah. And because your discriminator outputs probabilities for binary classification, in order to say that you want to make discriminator predict to understand that real classes are real and fake are fake, you will have something like this. Yeah, if we look at the losses, so loss for the discriminator will look like this, and loss for generator will look like this, which is actually in practice can be written in such way, which is a bit easier than this way. So instead of having 1 minus something, we'll have this stuff. Notice that common models don't actually train GANs in such way. There are some other loss functions which are kind of similar. One is called least squares GAN. So its name comes from least squares task. And instead of having this logarithm of something and logarithm of something here, they will have just a mean square error. So as far as I remember, it will be like d minus 1 squared here, and maybe 1 minus d j squared here. So something like this. And there is Wasserstein GAN, which is a bit more complicated and requires a bit different training scheme. But LS GAN and V GAN have much better properties, at least as far as I know, than the original version of two players game. You can go through these links at home and check what are the losses. Yeah, so to actually train your GAN, you need alternating algorithm. You need to train at first discriminator, then update generator, then update discriminator, and so on. So as I say, they will train each other. So,
So for example, in our example, when we are making from this smell spectrogram to a speech,
yeah,
which one of them, like, this means that a smell spectrogram will be a discriminator and another will be, which one, generator?
No. So, you mean here? So there will be one model in text-to-speech. There are two models. First one creates Mel spectrogram from text, another waveform from Mel spectrogram. To create Mel spectrogram from text, we will use a transformer-like model, which we don't explain, and this is a separate task. So we train one model just to do this transformation from text to Mel spectrogram without any wave synthesis. Then we forget about creating Mel spectrograms from text. We just use a data set with some audio. We will convert, we'll get the actual ground truth Mel spectrograms and train a separate GAN to actually predict waveform from Mel spectrogram. Your generator will predict waveform from Mel spectrogram, and discriminator will try to understand whether the generated waveform is real or fake. Yeah.
So once you've done all this training, you throw away the discriminator. Right?
Yes.
You just use the generator.
Yeah, discriminator is used only during training. Yeah. So one thing is to understand how it is done in PyTorch, because sometimes it gets complicated and you can get a lot of errors. Because you will try to. Usually, one mistake is that you will get is that PyTorch will say that you try to go through the same gradients the second time and return runtime error and so on. So the proper way to do training in PyTorch looks like this. At first, you will get generator outputs from your model, so your model will generate something. Then you will update your batch with these outputs. Just like as we discussed previous time, I like working with dictionaries instead of variables because it's much easier to process them. It makes code cleaner. Yeah. Then we have a separate optimizer for discriminator and separate optimizer for generator. We will do zero the gradients from discriminator optimizer. And we will calculate D outputs. Our model will discriminate between generated X and real X. And then we'll calculate some loss for our discriminator and do backward for this loss and optimizer step for discriminator. So at first, we generate outputs and update only discriminator. Then, after we update a discriminator, we should zero grade again gradients from J. Again, calculate the discriminate for updated discriminator, and then only then we can calculate generator output and do G loss backward. And I guess I missed here G loss G optimizer step. So there is a type here. There should be G optimizer step. One thing here is that notice that we in the first discriminate, where we update the discriminator, we need to detach the X here. So this means that the gradients from D loss dot backward won't go into the generator. So when we try to update discriminator, we don't want its gradients to go and do something with the generator. We will update generator in its own step here. So to avoid this, we'll call dot detach, which will detach computational graph from generator, and the gradients won't flow into the generator. If you don't remember what is detach, see the first seminar where I had a lot of examples with detach and what it means. Okay, questions? Yeah.
Using two asterisks before the batch. What's the difference between using two asterisks within the argument and just one asterisk?
I mean here?
No.
Asterisk is the commas, like.
This is the stars, I think they are actually.
Ah, this one?
Yeah.
Yeah, so in Python, if you have so first thing about asterisks and stuff, like if you have a function in Python, like some fun, you can define its arguments in two formats. First one is called ordered argument, something like this. So A, B, C, for example. Then you can have a keyword arguments, which are like D equal and some default value, default. E equals some another default. And what usually people do here, they say, instead of just having this, we can also have A, B, C, 1-star args, then D equals something, E equals something, 2 stars, keyword args. So this will mean that when I call my fun, I can say I pass A, B, C, maybe some other elements like 1, 2, 3, and then I pass D equals something, E equals something, and I can add maybe F equals something, J equals something. So when I will call my function, ABC will be ABC, D and E will be D and E, and args will be an array with 1, 2, 3. So it will be ordered arguments, and keywords will be a dictionary with these two new extra variables. So keywords will be a dictionary where F is equal to pass value, here it is E, and J will equal to another value here. Okay, so this is the first thing about stars.
So the double stars have to be strings and the other one have to be numbers.
No. So it's all about whether you have a keyword argument or ordered argument. So in args, you don't say what is the variable name. You don't say like it's A, B, C or something else. So here it can be like just an array 1, 2, 3, which you then access by args 0 to get 1, args 2 to get 2, and so on. But instead of 1, 2, 3, it can be anything else. It can be like, I don't know, like a string, then maybe 1, then maybe a whole object like PyTorch data set. And your args 0 will be string, args 1 will be 1, args 3 will be data set. And keyword arguments, instead of having array with args 0, it will have a dictionary where you should actually pass the variable name. So instead of having args 0, you will have keywords variable name, which is a string. And you will get something here. So
it seems like for the first one, order matters, or for the second, you just need to provide the kind of gallery.
yeah, we'll just provide the dictionary. You had some another question.
So for like A and B, does it mean that when you call a function, we need to specify like B equals something?
So if you don't write star args here, if you will have something like this, you can still pass, you can still call your func like func A, B, C, D, E, and it will automatically say D here, E is here. But if you have args here, it will be a problem with Python that it will think that D and E are inside args, not this D and E.
Right, because it doesn't know how long. There's no, the whole point of this, it's like args in C.
Yeah, the whole point of this is that you can pass any number of arguments here, and any number of keyword arguments here.
So like side that all it, yeah, say B equals something, B equals something inside.
So if I have an args, in order to change the value of D, I will need to use keyword here like D equals something, E equals something. If I don't have an args, I can still pass it in the correct order. Yeah, so the question about batch. So my batch here is actually a dictionary. It will have like batch will look something like this, like labels, some tensor, input, some tensor. And my forward function will look like this. It will be input, labels. So I can call forward using batch input, batch labels. So I can write arguments explicitly, or I can just say star batch and pass it and call it like this, like forward of this. And Python will automatically take a value from my batch, which has a key input, and automatically will take the element from my batch with a key which is called labels. So when I do such stuff, my batch should have the same keywords as are defined in my forward function. Okay? Good? Good. And one thing here is that if you have more keywords that your func requires here, what you need to do, you need to add star keywords here. So this can contain any number of elements. So if your batch has more stuff than input and labels, they will all be stored here and just not used. And that's what happens in PyTorch template that I showed you. Have a look. Yeah, yeah, hope we still have time. So conditional gains. Conditional gain, exactly the same thing, but apart from making stuff from noise, you have something to condition on. Maybe it's a class label, or maybe it's another image. So for example, you have a grayscale image and you want to generate a color image from a grayscale one. So you will condition on this grayscale image. So instead of just generating something from noise, your GAN will understand that it indeed should somehow base its prediction on this condition. Or maybe this can be like class labels, like a dog, a cat, and given some random noise and the label of a cat, your generator will predict cat, and given some another noise and class label dog, it will generate a dog. Something like this. And one classic architecture is called deep convolutional GAN. Just a lot of convolutions with upsampling here, which is done via constant transpose. I will show it in the next slide, I guess. So having a vector, you reshape your input to get something which is image-like, and discriminator will move from image-like representation to some binary classification task. We have one workshop on this with some code. I will put a link in the GitHub, and you can see like how it is implemented in code. It may be not the clearest code, but should be good enough. Yeah, and transport convolution, I guess Federico will talk about this on Thursday, but the idea is that we want to upscale our input, so we have a small input, and maybe we want to get something which is larger. We can do a simple B interpolation, how it is called, so some stuff from signal processing, but instead of this, we want to something with trainable parameters. So simple interpolation is just some signal processing stuff without any parameters, and maybe it's not the best choice to upscale our image. Instead, we want something with trainable weights, which will make upscaling a bit more precise. How it works, you have your input and you have your filter. Then your filter is multiplied by the first element in your input. And you will get something like this. Yeah, so if 1 by 1 is 1, 2 by 2 is 1, 3 by 1 is 1, 0 by 1 is 0. Then you will get another element, which is this filter multiplied by the second element. So 2 by 1 is 2, 2 by 2 is 4, 2 by 3 is 6, and 0 by 2 is still 0. Again, the same stuff for green, and the same stuff for blue, and the output of transposed convolution is just the sum of these these four elements. Okay. Yeah, and the size depends on the kernel size, so the filter size, on the padding, on the stride, all this kind of stuff. I won't go into more details today, but I hope the general idea is clear. Yeah, so upscaling occurs when we want to go back from compressed representation to the original one. We had this raw waveform. It is very long, but when we had a Mel spectrogram, it's much shorter. So in waveform, we have I elements. The same period of time, period of information has only J elements in Mel spectrogram. So we will use upscaling with constant transpose to upscale our Mel spectrogram. So its time resolution or time dimension has the same size as our waveform. And one example which we'll cover here is called hi-fi GAN, high fidelity, I guess it means. So your generator converts MEL spectrogram to a waveform. It looks like this. You have a lot of residual blocks applied one after another. So you have your input, you apply one res block, then the output is passed to the second res block, and so on. Each res block contains const transpose to upscale your MEL spectrogram, so to improve the length of your output, and so-called multi-resolution, don't remember what is ELF here, like maybe filter bank or something like this. And this MRF has another, this MRF contains these res blocks with different kernel size and different dilations. So you process your MEL spectrogram with various receptive fields. So each res block takes different contexts from a MEL spectrogram. And when you sum the output, you will sum the output from different contexts. And as a whole, you will process your model, you will process your input on different levels, use all sorts of information, and it allows you to get as high fidelity output as possible. Yeah, and each res block contains just standard res block with some convolutions and the leaky ReLU, like we discussed previous week on Wednesday. For the discriminator, Hi-Fi Gain has two discriminators. So two loss functions, there will be that are summed. One is called multi-period discriminator, and it analyzes audio on different periods P. So audio is a sum sinusoid, so contains some periodic signals, and you want to look at these periods to maybe see some periodic information in your audio. And what it does, yeah, it looks at diverse periodic patterns in the audio. So you have your 1D input, and you reshape it to have 2D matrix where the width is equal to P, and the height is just, it depends on the length of your waveform. So all these red dots are time steps which are period one from another, period time steps one from another. And you apply convolutional with the kernel k by 1, so you look only at one row of this matrix. You don't want to process it like this, so you don't want to process inputs from different periods. You want to process them independently. So your convolution has filter k by 1. This means that you on height you have a filter of length k, and on width you have a filter of length 1. So you process only sequences which are in one period. And basically, multi-period discriminator does just this. Another one is called multi-scale discriminator, and it analyzes audio on different levels with different receptive fields. So it allows you to capture consecutive patterns and long-term dependencies. So at first you process your whole audio input, then you apply average pooling to make it like 2 times shorter. And now you apply another convolution on this 2 times shorter input, then you apply 4 times average pooling, which decreases the length by 4. Apply another convolution, and so now you have 3 outputs: one on the like long level, one on the middle level, one on the short level, and you analyze your audio on different periods, or sorry, on different receptive fields on different levels. You captured long dependencies, you capture short dependencies, everything is fine. Yeah, and so you use these 2 discriminators, that's basically all. One thing I didn't mention here is that sometimes when you train GANs, you actually want to add some supervised losses. So that instead of having only discriminator loss and generator loss, you also have some other loss which can improve your generator or discriminator. For example, here your generator will produce a waveform. You know a real waveform for the same spectrogram. And what authors do, they add another loss which says that I want to minimize the difference between X real and X fake by some like L1, L2 norm. Actually, they calculate a CFT of this and calculate the differences in a CFT domain, but we can do it in waveform. It's not effective because they're much different. So it's better to do in a CFT, but the idea is the same. That apart from having discriminator and generator loss, you have some other supervised losses because you know the ground truth sample, and you can improve the quality of the predictions, but saying, okay, you predicted some fake image, but it should be actually as close to real image as possible.
But in that case, you have a predefined set of real samples, and those real samples are the ones you want to get close to. It's not a distribution.
Yeah. So hi-fi GAN is conditional GAN and actually without any noise. So some conditional GANs may work only on the condition without any noise, so they're not random in this sense. And in hi-fi GAN, you have a data set with audio, and for each audio, you compute the actual Mel spectrogram. Audio. Compute Mel spectrogram, compute via generator fake audio. And then you try to compare these two either via discriminator, or you can, for example, add L1 or L2 loss to just make this matrix and this waveform as close to possible in L1 or L2 sense.
And how would you use the generator if you don't? Because it seems like you already need a real audio sample.
Yeah, so when you train your generator, your MEL synthesis here,
Yeah.
you forgot about, when you train valve synthesis, you forgot about MEL synthesis and use real MEL spectrograms of an existing audio. So you don't train wave synthesis from text. You train it from real audio, and then when you want to create a text-to-speech model, you use one model to create text, MEL spectrogram from text, and another model to create audio from generated MEL spectrogram. Yeah, we have a bit of time. Yeah, one last task is called voice conversion. And it's just basically about me saying some sentence with some emotion, or maybe with my other properties. And voice conversion tries to preserve the content of the speech. So if I said hello, the output should also contain hello, but maybe instead of me, the speech will belong to some another human, like with some other emotion. Maybe I say something in a sad format, and the actual speech will be kind of happy. Yeah. So the idea is that voice conversion, that you will transform your speech to another speech with the same content, but the way it sounds will be different. Maybe I say something and I want it sound like it was the president's speech or some celebrity speech. So it's all about deepfakes here. And the common design is to have two networks. One will extract content from your waveform, from what you said. For example, this guy said, do you want to study PhD? And content encoder will encode this textual information into some matrix or vector here. Another model, which is called speaker encoder, will use another person's example utterance to understand what are the properties of this speaker, which makes it sound like this speaker, so like timbre, like pitch, and so on. And then you combine representation from context encoder and speaker encoder together to pass it through a decoder, which will use the voice of the speaker to say the text from the first speaker. So actually, voice conversion is an example of a task which combines two other tasks. Context encoder is basically automatic speech recognition. You want to get some textual information from speech. And speaker encoder is about voice biometry. So where you want to distinguish between this girl and this man, or like some other speakers. And one example based on hi-fi GAN that we discussed in previous slides is called hi-fi VC, hi-fi verse conversion. And it combines hi-fi GAN conformer from ISR, which we discussed, and a thing called variational autoencoder from voice biometry. So instead of YE here, it can be some other voice biometry model. We won't discuss it today, I guess, but it can be actually anything. And the idea is that from speaker one, you use ISR to get some textual information. You also use F0 calculation to calculate pitch. It's some signal processing stuff, not a deep neural network. And this is passed to hi-fi GAN generator, which is conditioned on the speaker encoder output. So hi-fi GAN generator will produce, because it's conditioned on the speaker encoder, it will produce the sound which sounds like speaker number 2. It will look like this. So you have source, you have mel. It is passed through ISR. You get one embedding. So from source passed to F0 calculation, which is then passed to some convolutions. You have another stuff. Then you sum these two. You have a decoder which is hi-fi GAN. You pass embedding from speaker encoder, and you result in a converted speech. And to train all this stuff, you have discriminators, because this decoder is a hi-fi GAN-like. You have reconstruction loss, which is basically what I meant here, so that real audio and fake audio should be close in like L1, L2 sense. And there is a speaker KL loss, Kullback-Leiber divergence, all this stuff. So it's just some loss to train speaker encoder. But I think you can use pre-trained speaker encoder and ignore speaker KL loss at all. Like train only F0 encoder and decoder. Yeah, and we have 2 minutes. I want to say what is autoencoder. So autoencoder is a general idea of compressing information. You have your input vector X, and your encoder tries to compress it into some latent vector Z. Decoder tries to get back from latent vector Z to something which is as close to the original input X as possible. So autoencoders another type of generative models. Autoencoder can't be used for generation because this latent vector doesn't correspond to the whole vector space. So if I just take a random latent vector and use this decoder, I won't get some new interesting output because model is not trained in such way. So latent vector here can be used only if it's output from some encoder. So we can't use generation here, but the autoencoders like this are used to compress information if you want to compress your information for some reason. Another thing is called variational autoencoder. So instead of predicting latent vector Z, we predict some distribution. For example, normal distribution, we predict its mean and variance. Then in order to get latent vector Z, we can just sample this vector from this normal distribution with the predicted mean and sigma. And decoder will try to reconstruct our input. And the idea here is that now we can sample any vector from this distribution to get any random Latin vector and use decoder to generate something. So YE sometimes is used for generation like this in order to enable making something generative, not just like this. And also YE in general results in a better quality as far as I know. Also, there is a thing called vector quantized YE. We won't cover it today. It will be something like this, but quantized version.